So let me introduce the speaker. We are very pleased today to have Dr. Changliu Liu. She's an assistant professor in the Robotics Institute at the School of Computer Science at Carnegie Mellon University, and she leads the Intelligent Control Lab. Prior to joining CMU in January 2019, she was a postdoc at Stanford Intelligent Systems Laboratory in 2018. Her research interests lie in the design and verification of human-centered intelligent systems with applications to manufacturing and transportation, and she published the book Designing Robot Behavior in Human-Robot Interactions with CRC Press in 2019. Her work has been recognized by NSF Career Award, an Amazon Research Award, a Ford URP Award, Advanced Robotics for Manufacturing Champion Award, Young Investor Award, and many other Best and Outstanding Paper Awards. So we're very pleased to have Dr. Liu with us today, so please take it away.
Cool, thank you. Thank you for the great introduction. And also it's my great pleasure to share with you some of our recent work in the certification of AI in robotic systems. Let me start from one video of our research that published last year, which is a human-robot collaborative system, where this robot equipped with a camera sensor look at the human motion, identify what the human needs, and then deliver the necessary work pieces and tools and hold it for the human to do the assembly. And we envision that with the development of AI and also the embodied AI recently, we will see more and more human-robot collaboration of this kind. And but then the core question we need to answer in our research is how can we make this type of human-robot collaborative system safe, especially when the robot is holding a hammer. We don't want the robot to hurt the human. And also due to the close proximity between the human and the robot, we want the robot to fully understand its the sensor limitations and also understand how its action will affect the human. And this is just one of our previous work, and then recently, oops, it's not showing. Recently, we have extended this human-robot paradigm into humanoid robots. As shown here, the humanoid robots, at the beginning, we teleoperate its motion. Because of a high degree of freedom, it can actually already be doing a lot of dexterous manipulations through teleoperation. And once the humanoid accumulate enough data, it can just learn from those teleoperated data and do the tasks autonomously. And that also poses significant question, like how can we make the AI system that kind of drive the robot's behavior safe, especially when the robot is holding a knife. We definitely need to make everything to be safe. Yeah, and you have, let me skip this one a little bit. Yeah, and how to do the formal certification. There are different ways, and a lot of people are doing fantastic research to do the certification of AI in robotic systems. But today I'm going to focus on two aspects, and especially two type of works that is generated in my lab. For all the robotic systems, the robots needs to be equipped with the perception skills and action skills. Perception is to understand what is in the environment by understand your camera input, tactile input, and the force input. And the action is to leverage the understanding of the environment and apply certain actions to change the state of the environment or change the reaction of human. We need to verify these two most important components in robotic system very rigorously before we allow the robot to deploy autonomously in the environment. For the perception, the most critical thing is how can we make sure the perception model is robust? And we'll talk about the problem formulation later. But action, the most critical thing is how can we make sure the robot is safe to its environment, especially to the human users, and also how can we make sure the robot is kind of safe with respect to itself. Yeah, so let's first look at the certification of the robot perception. So AI has been used for robot perception in multiple different ways. For example, we have machine learning models that do the object detection. We have machine learning models also do the image segmentation, as well as models to do keypoint detection. And here I'm going to share with you some of our current work on the certification for machine learning models that does the keypoint detection. And the surrogate or the SUT, system under test, is shown on the slide here. Yeah, it's a purely hypothetical like SUT. It's for the ease of public discussion and publication. In this system, the AI and the machine learning component is to estimate the pose of this airplane in the environment using a monocular camera. And the AI system first detects the key points on the plane using a ResNet. And then after the key points are detected, it will use a PMP algorithm to turn the key point into the pose estimation. Yeah, as we said, this is purely hypothetical, but this type of systems you can see a lot in actual deployment of like a real-world robotic system. For example, for robots to manipulate very complex objects, we need to first have a good understanding about the pose of the object and then decide how the robot should manipulate that. And to understand pose, a lot of people use this key point detection and pose estimation pipeline as shown here. So what can go wrong? If there's disturbances to the image, then a lot of things can go wrong. For example, here we're illustrating one type of disturbance, which is called channel drop. This like a blue channel, this is an RGB image and this blue channel got dropped. And now you see this image become like a very yellowish. And after the drop of this channel, we can see, although there's not significant change of the distribution of the key points, but all the key points actually kind of shrinked towards the center a little bit. So although if we look at each individual key points, the error is not that significant. But if we use this like a new key point to estimate the pose, the 60 pose of the airplane will be very off. Especially it will have large translational error as all the key points are shrinking to the center. Yeah, and this is problematic as we'll have a wrong understanding of the environment. And our work is specifically develop tools to verify that the trained machine learning model and the PMP estimation, post estimation pipeline is robust to certain type of perturbations in the real execution of this type of AI model. Okay. But before we look at our certification approaches, what are the standard approaches out there to do the certification of machine learning models? Usually there are just two types of approaches. One is using testing, one is using verification. There are differences illustrated in the figure here. So for machine learning models, suppose the model maps the input X to the output Y, and the model can be very complicated as shown in the black curve here. Testing is essentially, and our specification is to make sure for all the inputs in this orange curve on the X domain will be mapped to the constrained output set as shown in this blue region. So what testing do is to sample the input set and then see if the corresponding output of our model lies in the output set. It's very flexible and easy to implement, but the problem is that we might miss some of the peaks of the worst case behavior in the model. On the other hand, verification is an exhaustive approach which provides rigorous proofs of the network robustness, which essentially tries to falsify the property to see if there exists any X sample that maps Y to the Y region. Yeah, this can be done in multiple ways. For example, we can directly do the optimization-based falsification, or we can do the reachability analysis to see what are all the reachable output region given the input range. But all these approaches are currently operate image by image. We verify for each image it is robust with respect to certain range of perturbation. And then we create a full evaluation image set and run this evaluation or certification on all the images, and that will give us the final probabilistic certificate. And today I'm going to share with you how we can do the verification for this key point and the post estimation problem as shown earlier. So the verification for deep neural networks actually started, the type of research started many years ago. And starting from 2020, we have been organizing the VNComp, that is the international competition for neural network verification. As you can see throughout the years, we have been growing our benchmark problems in this competition, as well as we have been attracting more and more teams to join this competition. Yeah, but it's worth noting that for now, most of the benchmarks are still image classification problems, where we just taking the image and sometimes with low resolution and then create a label for it, whether it is a plane, whether it is a flower. For this very detailed key point detection network, there has not been a benchmark yet, or there has not been any kind of formal approaches to prove. And so then there's, in our research, we need to answer a few critical questions. That is, how can we kind of leverage existing formal verification tools for neural networks to verify this key point detection and post-verification, post-estimation pipeline? And the unique challenge for this problem is that we not only have a neural network component that performs the key point detection, but also a numerical optimization-based component, that is PNP, that is performing the post-estimation. How can we do the verification across these two? And the second is that in a lot of real-world use cases, we would like our model to be robust against semantic perturbations, such as channel drop or different weather environment, while existing approaches mostly defend against some random noise, which is bounded by some LP norm. And the last question is, if our current model is too complicated to verify, can we develop some additional approach to modify the model or retrain the model to make it easier to verify? So let's look at first two questions first by introducing our post-verification pipeline. So the pipeline here in the current slide is not yet verification, but it is the kind of nominal post-estimation pipeline, where we first taking a seed image and then run a neural network that performs the key point detection, which takes in the seed image and then output a heat map with the same size of the seed image that tells us like where the key point is likely located. And after that, we do a softmax to normalize the heat map and then use DSNT or argmax to extract the key point location. After we get the key point location, we then run the PNP algorithm to turn the key point location into a 6 degree of freedom pose of the plane. So that's the kind of inference, normal inference step. How can we do verification, especially how can we verify against semantic perturbations? Here, in order to do that, we introduce this convex Hall type of convex Hall based perturbation set. That is, we put the seed image as a vertex in our convex Hall and then add semantic perturbations to the seed image and then list those other images, perturbed images, as other vertex of the convex Hall. And this will form a range of image that can be viewed as a fusion of different perturbation, the fusion of different perturbed results. And after that, we can run the reachability analysis of the key point detection network over this whole set of perturbed image encoded by the convex Hall. And although there are several approaches that can support the reachability analysis on the image space, but it's worth noting that the current tools are still not that great in verifying against or doing reachability against softmax and also DSNT. And in order to deal with that, we did modify the network structure a little bit by turning the softmax to average pooling layer and do not consider DSNT. And then this will give us a reachable set. Okay, to provide you a concrete idea of what is exactly does this reachability analysis doing, it is visualized on this slide. So the left is the paradigm of the system architecture of our verification tool, which is called model verification.jl, which essentially runs the reachability analysis over a deep neural network. And the input to the reachability analysis or the model verification.jl is a convex Hall. of perturbed image set. Yeah, where one vertex of this convex hull is our original image. And here for simplicity, we just add a simple perturbation, which is removing some of the pixels here near the head of the plane. Okay, then we send these whole set of image into the reachability analysis tool. And through the layer by layer reachability analysis, we will get a lower bound and an upper bound on each neurons regarding the possible inputs in this perturbation set. And for those bounds, we first take an average, that is the center of the kind of output of the perturbed neurons, which the value is illustrated on the left. And also we take the difference between the upper bound and lower bound. Then it will give us kind of the range resulted from this perturbation at each neuron at each layer. So then we can do this propagation from the first layer to the last layer. As you can see, this GIF is essentially showing this forward propagation of this reachability analysis at the beginning. Let's wait a few seconds to see what is happening on the beginning. At the beginning, you can actually see, okay, here, the plane here, yeah, which is the, this is the center value. So at the beginning, we still have a lot of the raw image features. But as we propagate through the network, those raw image features get translated into high-level features. Yeah, so this is what is happening on the center of the reachable set. And on the right, we see the perturbation. At the beginning, the perturbation is actually very small, but as we propagate through the network, it got diffused to other parts of the neurons in the same layer. And in the end, we got a heat map like this. And as you remember, in order to deal with get rid of the softmax, we did add an average pooling to kind of reduce the size of the heat map, and then turn the verification problem into a verification over a finite classes. Yeah. But that's technical part. For this reachability analysis, what can we conclude? The major part is, or the conclusion can actually be drawn by looking at the heat map before the average pooling. So here, this is the center of the heat map. Essentially, the most likely key point location is here when we have the largest prediction. And then the perturbation in the input here resulted in a perturbation as shown in the blue region on the heat map. So from looking at these two figures, we can conclude that this current model, this ResNet 18, is robust to this single pixel perturbation due to two reasons. One reason is that the resulting perturbed region is far from the key point location here. Yeah, they're geometrically far, uncorrelated. And second is that if we look at the magnitude for the key point, the average prediction is 9, but the magnitude for the maximum perturbation is 0.0012. Yeah, so in this case, this perturbation is too small with respect to the signal range. So then the network is robust in this case. Yeah, and following the same reachability analysis pipeline, we can analyze all other type of perturbations. For example, what we have done is to remove the whole background of this image and add random perturbations on this background. And also we can add small objects on the image and see if the objects occlude the plane, what will happen. If the object do not occlude the plane, what can happen. And all of these can be supported by our verification tool called modelverification.jl. And it's worth noting that this tool is now the state-of-the-art tool, which runs much faster than existing approaches. Yeah, although I wouldn't say we did a very innovative algorithm design, it's mostly because we have very good implementation. Yeah, so we compared our tool with respect to 3 other award-winning tools in the VNComp on a aviation collision avoidance guidance control problem, ACAS-XU. And you can see for all instances, our model, the computation time is faster than the other models. Okay, so this constitutes the reachability analysis, but that's only the reachability analysis for the key point detection model. How can we then kind of do further reachability analysis to get the potential bounds on the post error? The issue is that for now, we don't have a good way to run reachability analysis over numerical optimization solvers. But on the other hand, we can do sensitivity analysis for any black box function and use that to correlate the input error bound and output error bound. So that's what we do. We actually run sensitivity analysis of the PMP. And in this way, we can turn the post error bound into the key point error bound, and then we can compare the allocated post error key point error bound with the reachable set computed using the neural network reachability analysis. Yeah, but currently there's one limitation, that is for turning the post error bound back to the key point error bound using sensitivity analysis. This is a purely statistical approach. We do not have very hard formal guarantee. The guarantee we have is probabilistic. So then in order to make sure that we do not introduce additional errors in the verification pipeline, we created a optimal allocation problem to allocate the allowable key point error among all key points into individual key points. And then we can create a buffer to shrink the allocation. So if we trust the sensitivity analysis more, we can have a larger allocation buffer. If we do not trust it, we do a smaller allocation. And then once we finish that, we can then check whether the reachable sets generated from the neural network reachability analysis belong to the allocated key point error bound. If it's, then we're done. If no, we can go one step further, that is to compute the largest allowable perturbation on the input set such that we can still have a satisfiable post error. Yeah, so that's the pipeline. And I would like to show you some of the results that we got by running this verification pipeline on CNN7 and ResNet 18. Yeah, so the architecture of these models are shown here. CNN7 is a bit small than ResNet 18. And we have altogether 24 key points. So we use the same key point detection backbone. And for the different key points, we'll do different pooling on the end, and then we flatten all the pooling and then concatenate. So then this will be a giant model that can allow us to verify 24 key points together. And these are the images that we use in the verification and also the corresponding key point error bound allocation. The post error is actually bigger than the requirement that we listed on the SUT page. But the reason for that is to create a fair comparison among different models. The CNN7 is taking a relatively low resolution image, which is 64 by 64. So then we want to make sure that the allocated key point error bound is at least 1 pixel big inside this a small resolution image. Yeah, otherwise it's hard to verify, or it's impossible to verify. And from that, we decided the post error bound, and then using the same post error bound, we allocated the key point error bound for the ResNet 18 model, which takes in a larger image, which is 256 by 256, and also it includes the 3 RGB channels. Yeah, but it's worth noting that the actual image used in the original problem is even higher resolution. And for now, we do see a huge bottleneck of applying the existing neural network verification approach to images beyond 256 by 256. The issue is that in order to go higher, to run reachability analysis for higher resolution image, we don't have enough memory to record the lower bound and upper bound for all the neurons in the network. Okay, so that's the problem and allocated key point error bound. And let's see how fast our certification pipeline could run and how accurate this verification could be, or how conservative this verification could be. Yeah, so we first show the result on the local object perturbation on the smaller network CNN7. As you can see, under almost all situations, the verification time per image is bounded by like 120 seconds, which is actually very good. And the verification time is smaller if we use a larger allocated keypoint error bound, which means we trust more about the sensitivity analysis of the PNP. Also there's a difference between the local object perturbation on the background only and the local object perturbation on the plane itself. Once we have perturbation on the plane itself, for example, adding some markers on the plane, the verification time definitely increases, as you can see from this one compared to this one, and these 3 bars compared to these 3 bars. On the other hand, with those perturbations, we still have good verified rate for the images we have. There are altogether 200 images. With larger keypoint error allocation and non-overlapping perturbations, the verified rate is higher than 80%. If we kind of use a smaller error bound, the verified rate drops, but some of the drop is actually due to the fact that the image is not robust to that perturbation. Yeah. And overall, this result is showing us that our verification approach is fast enough and also performant in terms of certifying the image. And we can also do global perturbations. And the mostly widely used global perturbations are the contrast change on the whole image and the brightness change on the whole image. And here we show some result on the global perturbation on ResNet 18. Although the range of perturbation is not super large, but we can still see the verification algorithm can still run within a meaningful amount, within a limited amount of time, and also give us a good verified rate. Yeah, and you may wonder, does the image property affect the verification runtime? Here is a slide showing that, yes, we believe it actually affects the runtime, especially when the image gets darker. As you can see, this is a result that is running over 3,000 images. We do the verification of CN7 over the brightness change or the brightness perturbation. Most of the images could be verified within 500 seconds. There are some images that requires longer time. As you can see, compared to those images that are easier to verify, those images are usually very dark. Yeah, and it's also our current research emphasize that is to understand what image feature that is affecting the verification efficiency. So with that, I hope I have convinced you that this is a good verification pipeline for the ML-based post-estimation method. It's computationally efficient and also performant. We do have a prior work, not our prior work, but prior work from another group from Imperial College London. Compared to this prior work, our method considers the post error directly, while the prior work only considers the keypoint error. And our method is efficient in the runtime, while the other approach did not report their runtime. Okay, before we proceed, I would like to pause a little bit to see if there's any question about the first part of the talk.
All right, are there any questions? We can bring a microphone to you if there are. I don't see any. So you have another part of your talk, or? Yes,
there's another part. Yeah, so the second part is how can we further improve the certifiability of our model through either design or training? Yeah, here we need to introduce a very important concept that is called certified robustness. That is the robustness of the model that could be verified, which consists of 2 parts. One is the true robustness. Yeah, true robustness meaning that if the if the model is truly robust, then there shouldn't exist any counterexample. But our verification approach is not directly evaluating the true robustness. It's evaluating a surrogate model of the true model. That is the surrogate model is somewhat linearized. Yeah, and then this leads us to the concept of certifiability. So if the original model is like a more linear, then it's more easy to be certified. If it's more nonlinear, then it's harder to be certified. And in order to achieve certified robustness, we actually need a model to be both truly robust and certifiable. To be truly robust, it actually requires the neuron to have smaller variance under perturbation. To be certifiable, it actually requires the neuron to be more stable under perturbation. Stable meaning that we should see fewer neurons that have values across 0 if we have value activation. Yeah, and with these two requirements, actually, if you're familiar with signal processing, it's actually the same requirement as increasing the signal to noise ratio of your neural network layer by layer, where the signal is essentially the center of the reachable set, which we have shown earlier, and the noise is the upper bound minus lower bound of your reachable set layer by layer. Yeah, so if you can increase the signal, and that means it's further away from the 0 point, then it's more stable. And if you can decrease the noise, then it means the neuron variance is smaller. Yeah, so essentially this is the reachability tool provided us a very good way to compute the signal and the noise ratio in the neural network. Yeah, but you may wonder, this is just intuition. Is that globally true that we can use signal to noise ratio to evaluate the robustness of a neural network? It actually is. So we did an empirical study. That is, we pull several models from this robust bench benchmark set. And yeah, so these models are already pre-trained and they have their empirical robustness evaluation as shown in the numbers here. And for these models, we then run our reachability analysis layer by layer and then compute the signal to noise ratio layer by layer. And as you can see from the plot, our SNR is actually a good metric and can be used to distinguish non-robust models from robust models. As you can see, the 0 robustness model always has a low SNR ratio. The high robustness rate model, the 67% robustness model, has the highest SNR. And also across the layers of the network, the SNR is actually increasing. That means the model is essentially learning to denoise the perturbations as we go deeper and deeper. So then this proves this SNR is a good metric. After that, we can then apply this good metric in the training by encouraging the signal to be higher and the noise to be smaller. Yeah, and after applying that in the standard training, we don't even need to apply that to the robust training. Very interesting phenomena happen. So on this slide, what we're showing is the layer by layer neuron-wise value, including their upper bound and lower bound under perturbation. So the first column is I think the layer 1 of this ResNet, second column layer 10, and then layer 19 and layer 28. For each layer, we rank all the neurons according to the mean value or the signal value. Yeah. And the index of the neurons are shown on the horizontal axis. And then the vertical axis is the value of that neuron. So we rank it using the signal value and then also plot the upper bound and the lower bound of that neuron. So as you can see with standard training methods, the neurons actually learned a lot of noisy behaviors around the 0 range, which does not have a good signal magnitude, also does not have a good a noise magnitude. With robustly trained network, the noise level got significantly reduced, which is good. But with our SNR trained model, plus some standard training metric, as you can see, not only the noise got attenuated, the signal also got enhanced. And also we do not have a lot of neurons that has cross-0 behavior. So that means the neurons are more stable. They're either always negative or always positive, which is good because then the model is more linear around that image and much easier to verify. And on top of this finding, we even introduced a pruning approach. That is, if some layers or some channels of the network is inherently hard to have good SNR, we just prune them out. And with that, we get three types of or three different models. The first model is only with standard training. The second model is standard training with the SNR loss. The third model is the standard training plus SNR loss plus 50% pruning. That is, we cut half of the network down. And then with these three models, we evaluate their conditional failure rate. So not surprisingly, with SNR training, the conditional failure rate is much lower with respect to the brightness change compared to the standard trained network. And the interesting result is that with the SNR trained model and even with 50% pruning, that is, the network is not as expressive as the original one, the conditional failure rate actually is as good as the standard trained method. Yeah, so this offers us like a good opportunity to think about, can we reduce our model to make it representative of the nominal behavior as well as the robustness behavior using these tricks like enhancing the signal to noise ratio as well as like using the verification tool to check the satisfiability. I believe there's a lot of we can do on this topic. Yeah, and that concludes my second part of the presentation. And I want to spend a little bit more time on a slightly different topic. That is, after we get the certified perception, how can we turn that certified perception into a certified action? For example, all the robots nowadays need to interact with the environment. So our humanoid robot needs to get to the field and move around in human-involved environment. Then how can we make sure they're safe? For example, if there's a bassinet, how can we make sure the robot will not knock down the bassinet? So there are different approaches to do that. The two most commonly used ones are doing barrier certificate synthesis. That is, for whichever objects we don't want the robot to get into, we try to synthesize a barrier function on top of that object such that there's a boundary of this barrier where once the robot touches, there exists a robot control to push it away. Then this creates a form of protection to the object that we do not want the robot to enter. And second approach is to do the reachability analysis, which is different from the reachability analysis of neural networks. It's more reachability analysis for a dynamical system that evaluates what are the range of locations this humanoid robot can go. Yeah. So for example, if there's a basal net we don't want the humanoid robot to get into, then we should prove that for the robot policy we have, all the reachable sets for this humanoid robot will not intersect with the unwanted region. So for simple dynamical systems, there are approaches to analytically derive the barrier function or reachable set. But for complicated systems like humanoids, there's no way for us to analytically derive it. What we need to do is to figure out a good way to numerically compute those certificates. And my group have developed a learning-based approach to learn this neural barrier function and neural reachability function. The idea is very straightforward. It's an actor-critic framework. Suppose our kind of reachable set or the allowable region is the area under this black curve. Then we first propose a reachable region as the area under the red curve. Then we attack the boundary to see whether this boundary exists some proper robot control policy to push the robot away from this unsafe region. If it does not, then we shrink our estimates, and in the end, it will converge to somewhere inside the safe region. So this approach works quite well in essentially in the simulation in the statistical evaluation. The issue is that now we are essentially using a neural network to certify a complex system. How can we even make sure that this neural certificate is good? Yeah, so then that brings us to the next big question about how to certify the neural action certificate. Yeah, here I'm just going to quickly show you some of our current results, and it is far from solved. And we believe there's a lot more to do in order for us to provide formal guarantees for those AI components in the robot action modules. So one work which is the work that is currently being presented in Coral this year, is that we then run the neural network reachability analysis on the neural certificate for this robot system. And how to do that? We just enumerate the boundary of the barrier function. And for each boundary box, we run a reachability analysis to show that there exists some control to push the robot away from this boundary. Yeah, as push the robot away from the basal net. This is a local approach, but it performs quite well. It is less conservative than existing approach, which it can show that this boundary here are satisfying by displaying this green color, where other approach is too conservative that cannot fully verify the problem. This is one approach, and the second approach is a more global verification approach. That is, we instead of like sampling the boundary and create a lot of little boxes on the boundary to do the certification, we can just form the problem as a falsification problem. That is, whenever we have a barrier function or a value function for reachability, what we want is that if we're currently safe, which means the value of the barrier is smaller than 0, the next step of the barrier should also be smaller than 0. That is, we are not get out of this non-safe region. Yeah, and then we can actually form a falsification problem. That is, if we can find some state of the robot that make our system, make the kind of dynamical system in the end enter into a situation that it is safe at the current moment but unsafe at the next moment. If that holds, then our barrier certificate is invalid. If we cannot find such state, then our barrier certificate is valid. And this can be solved very efficiently using mixed integer linear programming. And this is a global approach. It does not require us to sample the boundary of the barrier function. And we can even leverage this verification result to further fine-tune our model to of our barrier function or the reachability function to make it more robust. And with that, I would like to conclude with one last example. Let me see. Okay, it's not playing. Let me show the YouTube version. So in this example, we are actually developing a barrier certificate for this high-speed robot dog. So in this barrier certificate, we actually compute the reachable region for this robot dog. Yeah, and whenever the robot is near its boundary of the reachable state, it will slow down a little bit or even turn around to avoid further collision. It works quite well. This reachability function works quite well in the experiment, as you can see here. But after we do the formal analysis, we did find a counterexample, where the counterexample is showing here. Yeah, that is starting. So this is a simplified view of this robot dog navigation problem. This is the obstacle as shown in the red region. This is the goal the robot wants to go. And the robot is currently here. And under our current policy, the future trajectory of the robot is showing the blue curve. It will, in the end, bump into the obstacle. But our reachability function did not capture that. At this current location, it still predicts, okay, we're quite safe. And the safety value, quite safe, meaning that we're below 0. And the safety value get increased gradually until we bump into the obstacle, which is not good because it is too late to alert our system. On the other hand, after we add this verification and the fine-tuning, the updated value performs much better. At the beginning, it already predicts, okay, this is an unsafe state. And the future trajectory is marked as unsafe as well. So this creates like a more advanced alert to our system than the previous one, which also showcases the importance of leveraging verification tools to formally certify those neural certificates. Okay, as a conclusion today, yeah, it's my pleasure to share with you some of our recent work in the certification of AI for robotics. In particular, we look at the certification of perception as well as certification of action. For the certification of perception, we believe the most important question is how can we scale up the existing verification approach to larger networks, and also how can we improve the certifiability of the network. For the certification of action, the most important part is we actually need 2 layers of certification. One is a neural certificate to certify the dynamic system. Another is the certificate of that neural certificate. And it is needed to make these 2 certification pipeline work well together in order to generate a fully guaranteed autonomous system. And I would like to thank everyone for your attention and also acknowledge my wonderful students who did all the hard work behind the scene and also the sponsors. And with that, I would like to thank everyone. Happy to take any question.
Thank you, Dr. Liu. Let's next speaker. All right, are there any questions from the audience? Bring the mic to you. No? So I had a question about, you showed this video at the very beginning of this robot with a knife. A little bit terrifying, but is that something that you developed in your lab, this robot with the knife?
Yeah, that's our recent work. But while the robot is holding the knife, it's not running autonomous mode. It's the it's the teleoperated mode, and nobody is near the robot. The teleoperator is actually far from the robot. It's
okay,
just
so then what do you verify with this when it's cutting? What kind of things are you verifying that it's not going to do? Like you verify it's not going to stab someone or something like that?
Can you say that again?
So what are you like when the robot has this knife, what properties are you verifying that it is going to do?
Oh, great question. So if the we haven't verified that yet, but if we're going to verify that, what we need to verify is once the robot has the knife, it won't go anywhere else except for the current task that is cutting the cucumber. And when other agents or objects get into the scene, the robot should avoid pointing the kind of edge of the knife towards the object.
It should avoid pointing at anything but the object, I guess, right?
Yeah, that's true.
Okay, any questions? Other questions from the audience? Last call. Oh, we got one. Okay, bring you the mic.
So for key point estimation, pose estimation from key points, you showed the picture that when you remove the blue channel, it has some error. I don't understand. For key points, you look at edges, right? So what does coloring have to do with it?
Yeah, that's the parts we still need more understanding. So the ResNet is doing the key point detection, and it is totally like trained as a black box. So we are actually not sure how it tries to predict the key point. But during the test, we did find in a lot of cases the key point can be predicted wrong. It is not a kind of direct CAD matching problem. It's a pure data-driven black box learning problem. And for now, we lack the understanding. But the best we can do is still treat it as a black box, but add a verifier on top of it to make sure, given the perturbation, the output is good.
Yeah, thanks.
Mm-hmm.
All right, any final questions? Once, twice. Okay, then let's thank Dr. Liu one last time.
Thank you.